These are the homework solutions for AP Physics 1's homework number 4.2. So these are momentum and collision related questions, and we're going to start with a conceptual question, which is number 13 in chapter 7 of the Giancoli book. And that is a question about if two cars collide, what would you expect to be more damaging to the occupants? If they collide and stick together, or if they collide and rebound? So let's start with our quick definition of what would be damaging. So what exactly is damaging? Well, more force is damaging. So if these occupants experience more force, then they are necessarily going to be a little bit more damaged. So since we know that force is equal to the rate of change of momentum, then we just need to think about the fact that momentum change is related to how these cars collide. So based off of what we just learned, we have two main types of collision, elastic and inelastic. The first type, which is where they collide and stick, is inelastic. And for that case, if you think about it, the cars are going from some speed to some zero speed, and they stick together. And then for elastic, they are going from some speed to some speed in another direction. So in this case, delta V is going to be larger for an elastic collision. So since delta V is larger, we are going to have a bigger force because change in momentum is the same as m delta V. So a larger momentum change will come from this elastic collision. Therefore, an elastic collision will be more damaging than an inelastic collision. For question number 14, we have an elastic superball that's dropped from some height h onto a steel plate that's fixed to the earth, from which it rebounds at very nearly its original speed. So here's our ball. It's falling some height h onto essentially the ground. The question is momentum conserved during any part of this process? So the only way that momentum is conserved is if there's anything happening. So momentum is almost always conserved. The only situation where it's not conserved if some force is acting on our system from the outside. So the real question is, what is our system? So part B actually asks about that. It says, if we consider the ball and the earth as our system, during what part of the process is momentum conserved? So if we are talking about just the ball in A, then momentum is not necessarily conserved because gravity acts on it from the outside. So for A, there's an outside force acting on the ball. Gravity is that outside force. So momentum is not conserved for part A. But for B, momentum is technically conserved because the thing that's applying the force is inside of the system. So the earth force, which is the force of gravity, is now inside our system. Therefore, momentum is conserved. For C, it says, all right, now what happens if the piece of putty falls and sticks to the plate? So in this case, momentum is sort of conserved, but what's happening? Well, there's got to be some kind of force applied to it. And so what ends up happening here is that P is sort of conserved. However, what ends up happening is that energy is used to redistribute the putty. And truthfully, the earth actually moves a little bit when the putty hits it. The problem is that earth is so large, it doesn't really experience a big change in velocity. So you wouldn't notice it. For question number 16, we have a golf ball of mass 0.05 kilograms, and it's hit off a tee with a speed of 38 meters per second. So we're going to call this V final. If it's sitting on the tee, my initial speed was 0. The club touches the golf ball for 3.5 times 10 to the negative third seconds. And so we want to find the impulse imparted to the golf ball. So impulse is simply change in momentum, or mass times change in velocity, which we can also write as mass times v2 minus v1. So our impulse in this case is going to be our mass, 0.045, times our final velocity, 38, minus our initial, which is 0. So our momentum in this case will be simply 1.71 kilograms times meters per second. And that is our final momentum and also our change in momentum, since our initial momentum was 0. So this is part A. Now B asks us to find the average force. So from here we simply go to our other definition of impulse, which is force times time. So force then would be impulse divided by time. In this case, our impulse of 1.71 divided by our time of 3.5 times 10 to the negative third seconds. So our force in this case works out to be, we're rounding here, approximately 489 newtons. And there you have it, a simple impulse momentum question. For question 17, we have another impulse question. So I have a mass of 12 kilograms. I have an initial speed of 7.5 meters per second, and I have a final speed of 0 because it comes to rest, over a time interval of 8 milliseconds. I'm going to go ahead and make sure that this is in normal seconds, so that is 0.008 seconds, because a millisecond is a thousandth of a second. So question A asks for the impulse. So again, impulse is our change in momentum, or this is our mass times our final velocity minus initial. So our impulse will end up being 12 times 0 minus 7.5. So our impulse in this case actually ends up being negative, and that number is negative 90, and that's kilograms times meters per second. Now for part B, we want to find this force again. So impulse is force times time, and force would be impulse divided by time. So we'll have negative 90 over our time period of 0.008 seconds. So this average force ends up being a rather large negative 11,250 newtons. And I didn't round because this is actually a fairly nice number. So there we go. The negative is important because momentum is a vector. Question number 18 is a very tricky one because it's technically in 2 dimensions. So when I talk about my change in velocity, I need to be aware that not all of my velocity is changing. So when my ball hits the wall, the only force that's going to act on it is going to be straight to the left. So that means that only the velocity in the horizontal direction is going to change. So this is v in the x direction. So this velocity then we need to find. So v naught in the x direction is going to be v times, in this case we'll just use cosine or sine, it doesn't actually matter which, we'll use cosine, of 45 degrees. So that's going to be 28 times the cosine of 45 degrees. So v naught x is approximately, we'll say 19.8 meters per second. So now when we talk about our change in momentum, we're going to see, all right, I go in at 45 and I come out at 45, so my v final is actually going to come back at the same speed. Since we have the same speed, same angle, that means that v final in the x is going to be the same. So 19.8. So what's the difference? Well, we forgot to point out that one is to the right and one is to the left. So our final velocity in the x direction is actually negative 19.8. So now when we go in and want to find our impulse, we will do our mass times change in velocity, and that's going to be equal to, in this case, our mass of 0.06 kilograms times our final velocity of negative 19.8, minus our initial velocity of positive 19.8. So our impulse in this problem ends up being negative 2.376 kilograms meters per second. And if we want to be even more specific, we're talking about impulse in the x direction. So our impulse and our momentum change are only in the x direction in this case. For question number 19, we have a 25 kilogram astronaut. So we'll say mass of the astronaut is 125 kilograms. And they acquire a speed of 2.5 meters per second by pushing off with her legs from a 1900 kilogram space capsule. So we're going to say that this is V2A. So she acquires it during the course of this. So V2A is 2.5 meters per second. Meanwhile, V1A was 0. So the mass of our capsule is 1900 kilograms. Its initial speed was 0, and we are looking for its final speed, or its final velocity. So we're going to do this. We're going to find the change in speed by conserving momentum. So P1 is equal to P2. So we have MA times V1A plus M capsule times V1 capsule equals mass A times its final velocity plus mass capsule times its final velocity. So in this case, both initial momentums are 0. So what we end up having is the case where 0 is equal to our mass A, which is 125, or actually, let's do this symbolically. So we have mass A times V2A plus mass C times V2C, and we're going to solve for V2C. So we have negative mass A times V2A is equal to mass C times V2C. So finally, our V2 for the capsule is just going to be negative mass A times its second velocity over mass of the capsule. So substituting, we have negative 125 times 2.5 over 1900. So our final velocity for the capsule, and therefore its change in velocity, would be a rather small 0.164 meters per second, and that's negative. And so that is also our change in velocity, because it is going to react to her push. Now B asks us, if the push lasts 0.6 seconds, what is the average force exerted by each on the other? So since we have a change in velocity already, we can use our impulse to figure this out. So F delta T, and that's equal to M times delta V. So let's just pick one of our objects. So for the woman, we have, or the astronaut, I'm sorry, we have a force that would be M times delta V over delta T, and that would be 125 kilograms times our change in velocity of 2.5, which we were given to start with, over the time period of 0.06 seconds. So the force that she must exert would be approximately 5,208 newtons. And you could pick the space capsule as well if you liked, but you would end up with a different velocity and a different mass in this. So C says, what is the kinetic energy after the push? So the kinetic energy here is just going to be equal to 1/2, so let's do it this way. Kinetic energy of the astronaut is equal to 1/2 mass of the astronaut times her final velocity. So that's going to be 1/2 times 125 times the final velocity of 2.5 squared. So the final kinetic energy of the astronaut is about 390. So we'll write out the whole thing here. 390.625, and that's joules. And for the other, and for the capsule, that's going to be 1/2 mass of the capsule times its velocity, and that's 1/2 times 1900 times negative 0.164, and it doesn't matter we're negative because it gets squared. So the kinetic energy of the capsule just ends up being only 25.6 joules. So you can see that there's quite a big difference here, And this goes along with the fact that this is an inelastic collision. So energy is not conserved, so the energy of each will not be equal at the end. Initially, you will say that kinetic energy 1 was 0. So this is an important note that the kinetic energy was not conserved in this situation. For question number 21, we have a 95 kilogram fullback. So mass of the fullback is 95 kilograms. And they're running at 3.0 meters per second to the east. So V1 of the fullback is 3 meters per second. And they're stopped in 0.85 seconds by head-on tackle. So let's see, this is delta t. And so we know that V2 for the fullback is 0. So A, calculate the original momentum of the fullback. So this is easy. P equals mv. So our momentum is going to be 95 times 3, which is just simply 285 kilograms meters per second. Now part B says find the impulse on the fullback. So the impulse is the change in momentum. So we're going to do m times delta v, or m times v2 minus v1. So our impulse is actually going to be 95 times 0 minus 3. And so here, our impulse is actually going to be negative 285 kilograms meters per second, because our change in momentum necessary to stop this is to remove all of his momentum. C says, find the impulse on the tackler. Well, the impulse has to be the same, because the change in momentum must be conserved. For P to be conserved, that means that delta P must be equal to 0. So that means that the impulse on the tackler must actually be opposite. I guess we should say same but opposite sign. So for the tackler, it will be 285 kilograms meters per second. Now, D says, find the average force exerted on the tackler. So to do this, we have our J is equal to F delta T formula that we can rearrange to say J divided by delta T is equal to force. And our impulse is 285 divided by the time period of 0.85 seconds. So the force exerted on our tackler is 335 newtons. So just remember that according to Newton's second law, our forces are going to be equal but opposite. Similarly, our momentum changes have to be equal but opposite. For question number 22, we have a simple impulse question. And we have a newspaper with a mass of 0.5 kilograms, and it has to be thrown with a velocity of 3.0 meters per second. So this is V final, and our V initial was 0. So our impulse, again, is just m times our change in velocity. So we have 0.5 times 3 minus 0 for an easy impulse question that gives us 1.5, and that's kilograms times meters per second. Very easy question. All right, question number 25 kicks it up a notch. So we have a ball with a mass of 0.44 kilograms moving east with a speed of 3.8 meters per second. So we'll say this is mass A, and this is V1A, and this is 3.8 meters per second to the east, which is the positive direction. And it collides head-on with a ball at rest. So mass B is 0.22 kilograms, and V1B is 0. So after the collision, what is going to happen? Well, we aren't 100% sure, but we know that momentum will be conserved. So let's set up our conservation of momentum. So momentum is going to be mass A times V1A plus mass B times V1B equals mass A times its final velocity plus mass B times its final velocity. So our simplification is that V1B is 0, and that's all we know for sure. So now we can go on and we can say, all right, mass A is 0.44 kilograms times its initial speed of 3.8 equals 0.44 kilograms times whatever their final velocity is plus 0.22 kilograms times whatever his final velocity is. So let's go ahead and simplify this. So this is 1.672 equals 0.44 times V2A plus 0.22 times V2B. So I'm going to simplify this a little bit. I'm going to actually go through and I'm going to divide everything by 0.2, or 0.22 rather. And that's going to clean up my equation a little bit. And what that does is it gives me, on the left side, 7.6 equals 2 times V2A plus V2B. And this is really useful because I can go ahead and say that V2B is 7.6 minus 2 times V2A. Now, why is that useful? I have two unknowns, so I need another equation. And this other equation comes from conservation of kinetic energy, because this is an elastic collision. So we have 1/2 mass A times V1A squared plus 1/2 mass B times V1B squared equals 1/2 mass A times V1A squared, or sorry, V2A squared, plus 1/2 mass B times V2B squared. All right, so initial velocity is 0. Then we can get rid of all of our 1/2s. Now we can plug in some numbers. So mass A is 0.44, V1A is 3.8, don't forget to square, equals 0.44 times V2A squared plus 0.22 times V2B squared. So I'm actually going to go ahead and do the same thing I did up here, and I'm going to divide everything by 0.22 to clean up my equation. So what I end up with is, on the left side, 28.88 equals 2 times V2A squared plus V2B squared. Whew! So now I can do this. So V2B, I'm going to pull this down. If I want to square that, V2B squared would be 7.6 minus 2V2A, and then we're squaring it. So that's going to be 7.6 times 7.6, which is 57.76, minus, let's see, that's 2 times 7.6, so that's 15.2, and 15.2, which is 30.4 V2A plus 4 V2A squared. Okay, we're going to get rid of V2B squared with this. So that gives us 2 times V2A squared plus all of this mess. So 57.76 minus 30.4 V2A plus 4 times V2A squared. So we have to do some simplifying here, but we can see that this is a quadratic. So when we do that, we end up with 6 V2A squared minus 30.4 V2A plus 28.88. So this doesn't appear to be something we can factor, so let's go ahead and use the quadratic equation. When we plug this into a calculator, we have 2, so we have 1.267 and 3.8. So we have 2 choices here. All right, now which one is the one we want? So in order to figure this out, we can think about it. So is our final velocity, so this is for V2A, is it possible that our final velocity is 3.8? Well, not really. And the answer is it was a 3.8 to start, so we can't actually use the same one. So V1A was 3.8. So we don't want it to still be 3.8. So what we are going to go with is our 1.2667. So we can say V2A is equal to 1.267 meters per second, and that's there. And then we'll go in and say that, all right, V2B is equal to 7.6 minus 2 times V2A. So V2B will be 7.6 minus 2 times 1.267. So our final velocity for B ends up being 5.06, or we'll say 5.07 meters per second. So this is a rather lengthy algebra problem, but it is something that you are able to do. So this is the most difficult style problem you could potentially have, both on the AP exam and the coming quiz. But keep in mind, it does take a lot of time. So you do need to be kind of tediously careful and pay close attention to the algebra.